Click here.
Oh.
Okay.
No, I think so.
Okay, so thanks for the introduction, Georgios. So this talk is going to be about an algorithm called the iteratively reweighted least squares method, or IRLS, and its connection with an algorithm that we've seen in nature, in particular shown by this organism called the slime mole. And Georgios already explained the experiment. I'm going to talk more about it. And this is joint work with my student, Damien Strashak. So let me start by giving you an idea of what this algorithm is and what problem does it try to address. So imagine that you're given a system of linear equations. This system has this property that the number of variables is more than the number of constraints. So this is an underdetermined system of equations. And your goal is to find the sparsest solution. So such a system doesn't have a unique solution. And one way to enforce uniqueness is to say, find me the sparsest solution. This is a very common assumption, found both in engineering and sciences. In fact, it even has appearances in the brain. And so this problem shows up in many, many different areas, finding the sparsest solution for an underdetermined system of equations. So to formulate it mathematically, we think of a matrix A, which is an n cross m matrix. So think of m as much bigger than n. And the goal then becomes to find in this subspace Ax equal to b, find the sparsest vector. So we use this notation, zero norm. It's a non-convex function over this space. So unfortunately, this problem turns out to be NP-hard. And hence, we look for what kind of relaxations we can come up for this problem. So given that the norm is what seems to make it NP-hard, one way to relax the problem is to relax it to something which is more convex. In fact, very convex, the 2 norm. So we look at the problem of finding the least L2 norm vector in the subspace. So now geometrically, what this means is that you try to grow a ball around the origin until it hits this space of solutions. And the point of intersection is the solution. So L2 ball is not particularly nice for this problem because, as you can see, it's too convex. And so it's likely to hit at a point which is very non-sparse. So we are looking at either this point or this point as a sparse solution. It turns out that the next best thing you could do is to look at the L1 ball. So try to grow an L1 ball until it hits this space. And unless you're really unlucky, you're very likely to hit at the sparsest point. And this fact actually has been proven rigorously for a large class of matrices called RIP matrices, standing for restricted isoperimetric property, with these matrices. If they satisfy, then this is not really a relaxation. This exactly enables you to recover the sparsest solution. So even though the problem is NP-hard, with this additional assumption on the structure of the problem, this becomes easy. And the reason why it becomes easy, at least theoretically, is that the problem of finding a minimum L1 norm vector in a subspace, you can solve it using a linear program. Okay. However, this problem still has its attractiveness because to solve this, you just have to solve a linear system of equations. Okay, so compared to linear program, linear system of equations. Still, just because the problem has a polynomial time solution, in particular using linear programming, this is not what makes practitioners very happy for various reasons, which I'm not going to discuss in this conference. But there are issues like robustness, simplicity, and so on. And there are other methods that practitioners prefer to solve this problem of finding the least L1 norm vector in this subspace. And here, the starting point is this observation that the L2 minimization problem is very fast. To solve one step, all you need to do is to project the origin onto this subspace which is just solving a linear system of equations. Okay? And this leads me to the description of this method, which is called the iteratively reweighted least squares method, which solves this L1 minimization problem by reducing it to a sequence of L2 minimization problems. And this is a very old method, probably even going back to Gauss. And the method is pictorially in the following, that you start off at some point, let's say y0, and given that you are at this point yk, you use this point yk to scale or stretch the dimensions and then solve an L2 minimization problem to recover your new point. And this process, you hope, then converges to the optimal point that you're looking for. So mathematically, this is the precise way in which the points evolve. So given yk, you look at the ith coordinate of this current point yk, and you scale the ith coordinate inversely with this absolute value. Now, the intuition behind this is that if one of these yi is very small, or maybe even 0, then this puts a very large weight on this coordinate, and so you would not set it to non-zero unless you really need to do that. So once you are, it's a sparsity preserving or sparsity enforcing step. So at least heuristically it makes sense. Mathematically it's very simple, and implementation-wise it's really trivial. Even I can write a 3-line MATLAB code to implement this, and this is what you get. So here you see something which is in action as how this, so given the point, how the geometry is changing, and that's why the balls, instead of being round, are becoming more and more flat. Tall, sorry. And the process converges. So the question that we want to study is, given this dynamical system, when does it converge? If it converges, how quickly it converges, and so on. And just before I go on to giving you a little bit about the history of this problem, let me remind you that this problem actually captures some very important problems in computer science and optimization. So for instance, if I were to give you a graph, an undirected graph, where with a demand vector b, and I ask you to find a flow through the edges which has the minimum L1 norm subject to the demands, then this problem can be formulated in the setting of sparse recovery problem that we talked about in the following manner. And in fact, special cases of it are minimum cost bipartite matching, minimum cost flow, and so on. So these problems are extremely well studied in optimization, and in particular, you may ask, what does IRLS specialize in this setting? And the answer is a little bit cryptic, so people who already know this stuff will understand that each iteration of this IRLS specialized to the setting of graphs corresponds to setting up a resistor network where the resistances depend on the current y values. In fact, the higher the y, the lower the resistance. And you compute an electrical flow in this graph, and you repeat. So such algorithms have been used recently in coming up with many breakthroughs for fast algorithms for fundamental flow problems. And IRLS is one such algorithm which existed if you were to look at it from this point of view. So this is very similar. The point of this slide is to tell you that this is very similar, at least in spirit, to some of the very recent breakthroughs in flow algorithms. And in fact, this was my initial interest in understanding this method. So back to the convergence and complexity. Unfortunately, this method, this dynamical system, can get stuck in local periodic orbits and so on. And it's very easy to construct examples and starting points where this phenomena happens. So this is not a very nice thing for a dynamical system to have starting points where it gets stuck in non-optimal or non-global minima. And this is the case even when the problem is convex. And the real reason is that even though the problem is convex, the dynamical system itself is nonlinear and non-convex. And in fact, going back to the flow problem, if this was the flow polytope, then each vertex of this polytope acts as a local attractor. So there are some trajectories which will take you to each vertex, although there is one, and maybe if there is a unique solution, then there is exactly one point where all trajectories converge. But the fact that some trajectories take you to different vertices slows you down and is misleading and often traps you in local optima. So the convergence of this method has been a big open problem in this whole area, and there have been prior partial results by Ingrid Dobeschies and her co-authors, and more recently by Amir Beck. But the question about when does IRLS converge and how quickly does it converge kind of largely remains an open problem. So what do we do in this paper? So what we prove is the following, that the first observation is that this method is essentially the same as that you get to see when you see a slime mold operating inside a maze. Okay, so this algorithm makes an appearance in nature. Now this might just be a curious fact for many of you here, and it's not clear why this is an interesting thing and why should we care about it. The reason why this is interesting is that this connection between this method and the working of slime mold, and given some prior work on the analysis of slime mold which we had, allowed us to analyze this method by relying on the physical intuition which guides this biological organism. So analyzing this method is tantamount to coming up with the right potential functions or Lyapunov functions to understand what are the right quantities to look at which prove convergence. And concretely, what we can prove is that this method, or something which I will define in a second, the damped version of this method, comes 1 plus epsilon close to the optimal solution in something like 1 over epsilon cube steps. So here I'm only focusing on the dependence on the error. So 1 plus epsilon multiplicatively close to the optimum in about 1 over epsilon cube steps. Of course, the number of iterations also depend on the precise properties of the matrix. And in particular, if you care about the min cost flow problem, we can get a convergence of something like n over epsilon cube. Number of iterations. Each iteration is computing an electrical flow, which we know by the results of Spielman and Thing can be done in near linear time. So this gives you an algorithm for solving the min cost flow problem in roughly mn by epsilon cube time. Okay.
Wait, so does this match the performance of the previous algorithm? Or?
No. Yeah.
But it's slime mold.
It's slime mold. It's very easy, and you know, so one hope is that these kinds of methods can potentially have other properties like robustness and so on. Yeah. Okay, so now let me tell you this first part of the story about how and when this method arises in nature. And here I'll show you a very short and quick video. Georgios already described the whole experiment, but nonetheless, let's see if it works. Here you can see a maze. It's really a small thing. So what you're seeing is a very magnified image of this organism, and you see two places in the maze. Oats is provided to the slime mold, and slime mold really likes oats apparently, as you can see. And very quickly, at least in the video, it's a time-lapse video. Okay. So I used to have a longer version, but given the talk is shorter, I found even a shorter version. So this finished even before I could complete. But so as you can see that it did something. It did some kinds of, the flows went around, and eventually it converged to the shortest path in the maze between the two food sources. And this is not a one-off experiment. This has been repeated many times in many mazes, except that the Quaker oats remains the same. So that's something I guess one has to try. Okay, so this experiment appeared in a paper by Nakagaki, Yamada, and Toth, I think in Nature in 2000. Generated a lot of excitement, and a mathematical model of this was presented by Teiro Kobayashi and Nakagaki. And roughly, the biology behind this model are these phenomenal tubes that nature or evolution has endowed this organism with. So each of these tubes have this ability that depending upon the flux of the flow, the fluid that is flowing through it, it can regulate its diameter. Okay? And mathematically then we can think of the slime mold in a maze as a collection of interconnected tubes where tubes could have different diameters at different times, and this then evolves over time in a very precise manner, which I'm going to tell you in the next slide. So qualitatively, the local behavior of the system is that if the flux is large compared to the diameter, then the diameter increases at the next time step. And if the flux is small compared to the diameter, then the organism tries to economize and it reduces its diameter in the next step. Something very natural. That's something that you would expect. Even you would do it if you were a slime mold, I guess. So, so one can write down a differential equation which captures precisely the relation between the flux and the diameter. So sigma is a vector of diameters, and this is a system of coupled differential equations where for each edge, the diameter, the rate at which the diameter is changing is equal to the magnitude of the flux minus the current diameter. Okay, so at least one thing is clear, that if this number is positive, which is the case when this is bigger than this, then the diameter increases, and otherwise it decreases. So you may ask, what is the relation between flux and sigma, the diameters? And to explain that, it's convenient to think of the graph as a collection of so the collection of tubes as a graph, and at any time t for this edge E, you have the sigma ET, which captures the diameter. And you can write down the edge vertex incidence matrix for this graph. Take the demand vector to be +1 and -1 at the two food sources, and using some fluid dynamics, which I'm going to skip, but basically some elementary physics arguments, you can prove by a variational argument that the flux is the solution to this optimization problem. So this is really the connection between, I mean, if you look at this equation, this is precisely the same as, at least in form, is precisely the same as what we saw for IRLS. And this is, this is just, in the world of electrical flows, this is just Thomson's energy minimizing principle, which says that electrical flows minimize energy and so on. And in the world of fluid dynamics, this also has a very precise meaning. Okay, so with this setup, it's now, let me now tell you the connection between these two dynamical systems. And to make this connection a bit more precise, we need to introduce a new parameter, which is a number, h, which is something that you think of between 0 and 1. So one of the issues between, when you want to reconcile this dynamical system versus that, there are two issues. One is the notion of time. In one case, in the case of slime mold, the time is continuous. In the case of IRLS, the time is discrete. And the second is that these set of variables are not directly related to each other. So you can try. I mean, it looks the same, but when you try to fit in, there's no exact matching. So the notion of time we will fix by introducing this parameter h. In fact, think of h being 0 is like continuous time, and h being 1 is like discrete time. Okay? And what we will do is we'll construct a dynamical system which has variables both which belong here and there. So a dynamical system with twice as many variables, so that each of them will appear as a projection of this metadynamical system. And here is the metadynamical system. So it maintains two sets of variables as promised, y variables and w variables. So if at step k, y and w are the current variables, the first thing you do is you solve a least squares problem with respect to the weights. And once you have solved the problem with respect to the weights, you update the new weights by taking the convex combination of the old vector with, in the case of the y variables, the signed flow, and in the case of the weight variables, with the unsigned flow values. So this is a little bit, I mean, if I just show you this, it would not make sense. But now it's easy for you to see that if I let h equal to 1, and I ignore the w variables, then it gives me precisely the IRLS dynamics. And if I let h tend to 0 and I ignore the y variables, I get this slime mold dynamics. So two opposite ends of this h spectrum and two different sets of variables. So this is what we call the damped IRLS. Damped because h can neither be 0 nor be 1. It is something in between. Nonetheless, the solution converges to the right one. So what we do is we really give an analysis, convergence analysis and time complexity analysis for this meta algorithm, which then in turn implies something for IRLS and Fusarium dynamics. And this analysis, as I hinted in the beginning, is motivated by looking at or coming up with potential functions which are very natural in the setting of slime mold dynamics. I don't have time to explain you how, but well, energy is one thing that you can associate to the current state of the slime mold, or in terms of the amount of flux energy it is dissipating. And also you can define a very natural notion of entropy, or relative entropy in this case, between the current set of solution, which is captured by these weights, and the optimal solution. So X star is the optimal solution. So in these, with these potential functions, essentially there are two cases which show up, and I guess Giorgio's already signaled me, so I'm going to save you the trouble of taking you through these diagrams. But roughly there are two cases, and in both cases we can show at least one of the potential function. You make progress in at least one of the potential function. In the first case, one can show that the cost reduces, and in the second case, one can show that the gap between energy and optimal reduces. Okay, so these are some equations. The proof is not difficult. I mean, it's really a couple of pages if you know what you're doing, and bear some resemblance to the multiplicative weight update method. So I just want to conclude with what my experience has been with this slime mold dynamics. I've been working on these dynamics for about a year now, and we have found connections between, or rather dynamics inspired by the slime mold for three different and important classes of problems. One is a case of network flows, and one is a case of linear programming, and one is a case of sparse recovery. So this is the talk I gave today. These are three different pieces of works. And interestingly, in all these three cases, we connect with three very basic and very interesting methods to solve these problems. So in the case of network flows, as we saw roughly, that we make connections to electrical flow-based algorithms. There is a certain dynamics called the directed dynamics, in which case we make connections to the well-known interior point methods. And then you saw today the connection between IRLS. What we have done is taken the first few steps to prove correctness, to establish some basic complexity bounds, and it remains to prove how good really they are, or can they lead to faster algorithms. So clearly they have properties which are beyond fastness, simplicity, robustness, and so on, and there are many things which probably are left to be explored about these algorithms. And with this, I'd like to thank you for your attention.
Any questions?
So is that IRLS cryptocraft in local in non-optimal solutions? Can the Vishnoi dynamics network?
No, the Fusarium dynamics is very clever, and that's why it takes very small steps. So the fact that it seems to continuously evolve in time, so it really slows down the time. So it's not so aggressive in taking steps, and that helps it in not getting it trapped in local optima. I mean, from an algorithmic point of view, you would want to be aggressive.
We're a bit over. Actually, we should just call it a day.
Okay.
Let's thank all the speakers again.
Thank you.